Great. Hi, everyone. I'm Nikhil, and it's my pleasure to chair this session on behalf of the program chairs, Andrew Goodman-Bacon, Liz Bondi, and myself. Yeah, so this is the the best paper session. We'll have two wonderful talks later on in the session, and so I just wanted to say a few words before then. So a little bit about the award selection process. We started with the reviews and then area chair nominations, and then the program chairs, and then the executive board representatives for the conference read a short list of the papers and then discussed. And for various papers, specific members had co-authors and so on, and so recused and did not participate in discussions for those specific papers. And then from that, we ultimately selected a set of awards based on the reviews, the feedback, our own reading and discussion, and with the goal to highlight the diversity, broad set of work and methodologies and areas from throughout the community. And as always, many more deserving papers than we can highlight. But really glad to announce we had 3 honorable mentions that I think we've seen presented or will see presented throughout the conference. The first one, fair decisions through plurality, results from a crowdfunding platform. The second, be intentional about fairness, size, and multiplicity in the Rashomon set. And then finally, digital pulse of development, constructing poverty metrics from social media discourse. And with that, we're going to hear 2 wonderful talks from the Best Paper Awards. The first one is Optimization Meets Participation, Iterative Zone Generation for School Assignment. And the second in the session, Identity-Related Speech Suppression and Generative AI Content Moderation. And with that, Irene, do you want to come up? And I will try to set up your slides. Or he will set up your slides.
Well, thank you to the organizers for organizing such a wonderful conference that's been full of very excellent papers on very important and meaningful topics. And so it's really such an honor to be selected as one of the best papers amongst such an excellent set of papers. It's my privilege today to tell you about our work on optimization meets participation, iterative zone generation for school assignment. And this is joint work with my former PhD students, Katherine, Mentzer, and Mobin, YahyazadehJeloudar. Okay, so the context I want you to have in mind is student assignment, that is assigning students to public schools in a particular school district. This is the San Francisco Unified School District. I'm going to abbreviate it as SFUSD for short. And I want you to think about incoming kindergarten students, so about 4,000 students applying to about 150 programs at about 70 schools. And San Francisco is one of many school districts that uses something known in my field as school choice, a little bit different to the common use of the term. This means that the students can apply to any of the programs amongst those in the district, and then we use an algorithm to assign students to schools. Okay. And so why was there a need to redesign student assignment in San Francisco? Well, like many school districts across the US, SFUSD is very residentially segregated, and the schools are also very segregated. So what I'm showing you here is socioeconomic segregation in the district in 2018 as measured by eligibility for free or reduced price lunch. This is a common measure of socioeconomic need in the education literature. And I'm showing you 2 things here. On the background is a heat map showing the percentage of students who live in an attendance area who are eligible for free or reduced price lunch. And then on top of that, the red dots are the 50% of schools that have the highest percentage of students attending the school. who are eligible for free or reduced price lunch. And so you can see two things, right? There's a clear geographic pattern. There's a sort of geography of segregation. There's sort of more so students with socioeconomic need who live here in the southeast corner. And then there's sort of the rich areas in the northwest. And the schools with high socioeconomic need are basically right on top of those areas, even though San Francisco has since 2011 been using a district-wide school choice policy that allows students to choose from schools that are not exactly where they live. Okay, so motivated by this and other issues, in 2018, the San Francisco Board of Education initiated a redesign of their elementary student assignment policy toward 3 goals. Those goals were explicitly to improve diversity of the schools, to improve proximity, so students wouldn't have to travel sort of really far away from home to go to school, and then also to improve predictability, so students have a good sense of where they're likely to be able to go to school, and also to make the system sort of more transparent and less confusing. And so since in 2018 through 2020, my team worked with some staff at the San Francisco Unified School District to design a new policy for student assignment that was then approved in 2020. And so what I'm going to do today is tell you about some follow-up work. What do we do after this policy was approved? To do that, I'm going to tell you a little bit about what the policy is. Okay, so currently, we're still using the old policy. We actually haven't transitioned to using the new policy. We're in what they call the policy implementation phase. And so the current policy, as I mentioned, is district-wide school choice. Students can rank any of the 150 programs in the district. Schools give priority to students, depending on things like, do you have a sibling at the school? Do you live in that attendance area, that neighborhood around the school? And do you live in an area that historically has low test scores? Those students are given high priority at all the schools. In addition, that sort of just gives you these course orderings of students. And so the schools break ties randomly when there are ties between students. And then these preference rankings from the students and priorities from the schools are put into an algorithm known as the deferred acceptance algorithm. And that's what tells the students which schools they get to go to. And so what is the new policy? The policy approved in 2020 is one of controlled choice in multi-school zones. So what do I mean by this? The first piece, the new piece, is zones. And so what I'm going to do, you can basically think, instead of having one huge district where I'm choosing from everything, I'm going to subdivide it into smaller districts. Okay, so these districts are going to be defined by geographic boundaries, and each boundary is going to circumscribe an area that's going to have multiple schools. And so you get to choose now, not from all of the schools, but just from the schools in your zone of residence. Okay, there are some exceptions for special programs like language, so on and so forth. In addition, this is not necessarily going to help with diversity. And so one of the main things that we showed in the previous work was that you can control choice within the zones by reserving different fractions of seats for students from different backgrounds. And this is going to help you toward these diversity goals. Okay, so that's all the background. And so the main question we're going to try to address today is, well, what zones should we use? And more importantly, how do we design these zones sort of together as a community, not just sort of impose zones from top down? So this is a very challenging problem. I come from a more computational background, and so the first thing that someone from an operations research background will notice is that districting or zone design is a computationally hard problem. Okay, so that's very related to neighborhood zoning, political redistricting. These are all NP hard problems. And there's a rich literature of using computational techniques to solve those 2 problems, but a little less on multi-school zones. And actually, multi-school zones is even harder for a couple of reasons. First, compared to neighborhood school zones, where not just the zone doesn't define who goes to the school, there's still choice within the zone. And then compared to political redistricting, something that was very important, especially toward diversity goals, is to look at, well, do we have representation amongst all these different demographics? And so you might look at, well, do we have representation for white students, Hispanic students? You might also look at, do we have representation for low SES, high SES students coming from those different backgrounds? Okay, and so this means that we have a lot of potential objectives or a lot of potential constraints, which is quite different from political redistricting, where there's sort of one binding constraint of having population balance. I mentioned before also that we wanted to come up with these zones in a very participatory way, and so this raises all kinds of participatory challenges. I would describe school zoning, student assignment, all of this as sort of a wicked problem. So this is a term coined to describe these problems that are just within the social policy space that are super gnarly for a lot of different reasons. One of these reasons is that there are complex social interdependencies in the problem. And so for us, it really motivated that we have to allow all different stakeholders to participate in the zoning process. Okay? And so I could talk a lot about the ways that we can make optimization more participatory. There's quite a bit already in the operations literature. And I just want to call out that previously in school operations, usually what's offered is some kind of decision support that's used primarily for the decision makers, so sort of district leaders. But there has been more examples of involving broader stakeholder groups, for example, in the districting paper that we saw yesterday. And also the other thing that I'll be drawing on is this really cool new possibility we now have to use LLMs to kind of help people who don't really understand optimization to still interact with optimization using natural language. Another feature of wicked problems is that they're very hard in the sense that it's hard to define what the problem even is before seeing a solution. Now, actually, in the context of zoning, especially zoning for, you're not just deciding what school goes in the zone, you're deciding sort of like a set of schools, but then you don't really know, like, does that mean I get to go to my favorite school in the zone? It kind of depends on what everyone else in the zone wants. And so actually, it's hard even for an individual person to define, like, what zones do I prefer, right? And so there's a lot of literature, even on this problem of preference elicitation, right? How do we help people figure out what they want in these super complex problems? And sort of our takeaway from all of this, and also from talking with district staff and other stakeholders, is people kind of need to see zones to be able to participate in deciding on zones. Okay? And so that actually makes the computational challenges and participatory challenges like very interconnected, right? Because I need to show people a lot of zones if I want to give them a chance to really participate in designing zones. And so I need to be able to generate a lot of zones very quickly. Okay, so hopefully you can start seeing with this sort of interconnection the approach that we're going to take from this for this problem. We call this optimization meets participation. And basically, we're going to have this iterative framework, which has three main parts. The first is we need to develop these faster computational methods specifically for this problem of optimizing multi-school zone boundaries, given sort of different preferences that people might have. And we're going to encode those preferences specifically using constraints. So I'll be more precise later. Then we want to let people sort of explore, right? Say, well, you showed me this set of zones, and this is meant to sort of be zones that are better for diversity, but not so good for proximity. But actually, I want to have smaller zones. I want my schools to be close to home. What does that mean for what the zones look like? And so we sort of have this back and forth process where people can see zones, react to them, and then we use that to update what the zones look like. Okay. And then finally, we worked quite hard to try to combine the choice into the optimization of zones. We have a formulation. It's just that this formulation doesn't run. And so it's sort of too big an optimization problem. And so we just split that up into two separate pieces. We first do the optimization without taking choice into account, and then we simulate choice and take a look at post-choice metrics as well. Okay, So with that, let me tell you a little bit more about our optimization and participation methods. So the general computational approach to zone design is to put together building blocks, geographic building blocks to generate zones satisfying certain size, shape, and balance constraints. And I'm going to tell you about two approaches that we did in the paper. One is using multi-level optimization, and a second is using sort of sampling techniques that are proving very effective currently in political redistricting. Okay, so a little bit more about these. As I mentioned, these approaches put together smaller geographical building blocks into larger zones. And so let's say I have some geographic unit U, and then I have a specific zone Z. And in our case, we sort of seeded the zones with like a popular school. Okay, so we have a set of popular schools, and each of those is going to be a centroid of a zone. Okay, and we had lots of different possible sets of popular schools that we could use to seed. And so we have a decision variable x, u, z. That's going to be 1 if unit u is in zone z and 0 otherwise. Okay, and so then you can write this as a mix and program. You put in some feasibility constraints. There are some different ways that you can do zone contiguity. The main thing I want you to focus on is that we actually have a lot of different balance constraints. Okay, we have balance of students across zones, students in the number of seats in the zone, demographic balance, also balance of school performance or popularity across zones. And you might have some, you might want all of these to be perfectly balanced, but that's not going to be possible. Right? And so what we do is we put these sort of thresholds for how far are we from perfect balance. And so for example, how far are we in each zone from the district average eligibility for free reduced price lunch. And these are the things that we're going to allow our stakeholders to kind of tune. And we do this rather than looking at weights in the objective, as was done in the paper yesterday. This is sort of aligned with some previous preference solicitation work where we find that people kind of react better to find it more interpretable. To think about constraints like I want to be within 10% or 15% of district free reduced price lunch eligibility, rather than like I 50% care about diversity and 25% care about proximity. And this is true with when we were interacting with our different stakeholders. Okay. And so one question you might have when generating these zones is what size units should we use? And so in the original policy paper, what we did was we used attendance areas. There's about 60 attendance areas in San Francisco. And so this is a very tractably sized problem. Depending on how many zones we want to split the district into, that takes about 1 to 20 minutes to run, just the standard formulation I showed you before. The problem is, if we're trying to finalize zone boundaries, then we want to be a lot more fine-grained in how we're putting together these zones. And so you might think, oh, I can use census blocks, right? So that is 2 orders of magnitude more. There are now 6,000 units. Unfortunately, if we just try to solve this using the formulation we used before, it doesn't solve for anything more than 4 zones. Okay, just keep running, doesn't find anything. Okay, and so what do we do? Our first approach is a multi-level optimization approach. And so I'm just kind of show you how it performs or how it works using pictures. Okay, I'm going to start with an initial solution. This is one that I built using the big building blocks. It looks something like this. You can see the big building blocks are not great because you get these like weird shapes like this bit over here. And what I'm going to do is I'm going to freeze the middle of these zones that I created with the big building blocks. And then I'm going to sort of trim out the edges. And now I sort of have a smaller size problem that I can solve using smaller size blocks. Okay, so now I solve for these trim parts using, you can see here that the unit I'm using now is census block groups. So there's about 1 order of magnitude more of those than attendance areas. I solve, and then I trim again, and now I can go down to just the census blocks and solve at the census block level. Okay, and so I do those steps. I do some sort of local search where I'm sort of trying to improve the boundaries even more to make the zones nice shaped. And you can see I go from something that looks like this set of zoning map on the left to the zoning map on the right. Looks a lot more like something you might actually use. The second approach that we did, this one was more directly applying something that already exists in the literature. And so what we applied is something known as the relaxed recom approach. And so this is a method that's very effective for sampling a lot of different possible zonings in a representative manner. And the relaxed version actually has a provably fast mixing time. Okay, so it can sample these quite quickly. Okay, and so here's how it works. First, you start out with your zoning, and you pick 2 adjacent zones randomly, and then you just merge them. Okay, you have this mega zone, you're going to try to resplit it. How do you resplit it? Well, we're going to sample a random spanning tree of the merged zones. And now I'm going to select one edge in this spanning tree to cut. Okay, and what relaxed recom does is it says, I'm going to select this edge using a biased spanning tree distribution. Whereas recom, which was not the relaxed version, just sort of sampled the edge uniformly at random. Okay. And then finally, you cut this edge and you get zones. Okay, and I'm going to keep doing this. And so each time I do this, I sort of am making quite a big step across the set of possible zones, because you can see that the initial zones and final zones might be quite different. Okay. And so what we did was we just observed that this is designed for representative sampling, but what we're trying to do, we're not trying to do representative sampling, we're trying to find good zones. And so maybe can we nudge toward good zones by sort of doing something with this bias spanning tree distribution. And so we did something pretty heuristic, and just to see if it would work. That was the optimization part. Next, we have participation. And so we had 2 rounds of user engagement so far. The first round, even before all the iterative process, was just to figure out, well, what are the metrics that people actually care about in this problem? And so to identify these metrics, we ran 6 focus groups with San Francisco staff, both at the school district and other city agencies, as well as with parent leaders. And just to give you a sense, it would look something like this. We'll show them some maps and then ask them a bunch of questions for these maps and sort of these like structured discussion sessions. Okay, I'm not going to go into details, but the things I'm highlighting are too light, so you can't see. But basically, some of these questions over here are specifically about geography. Okay. Some of the questions over here are specifically about the data that we're showing specifically about the stated policy goals from the 2018 board resolution and the 2020 approved policy. And then we also had a bunch of questions for open-ended feedback, right? And so we were just trying to sort of get a sense for like what kinds of things should we be including in the objectives and constraints. Okay, so this was sort of the initial round of community feedback. And I would say that is probably the more common way of engaging with the community. In optimization, you sort of involve people when you're first modeling the problem. And so the more sort of in my opinion, innovative part is the second part where we're actually iterating. Because the problem is, as I said before, people kind of need to see zones to really be able to tell you what they want. Okay, and so what we do is we iterate back and forth between generating zones and showing them to the stakeholder to help them kind of build this consideration set. Okay, you get a sense for what's possible with zones. Okay, and once they have this consideration set, what's possible, then we ask them, which are your favorite zones? Okay. And so what does this consideration set look like? Well, we'll show you a feasible zone maps given a certain set of constraints. Okay, and so from our perspective as optimizers, this map corresponds to this point in constraint space. Okay, this is just for illustration purposes, 2 of the types of constraints. This is the diversity as measured by deviation from district eligibility for free reduced price lunch, and down here we have shortage. This is sort of the balance of seats and the number of students in the zone. Okay, and then we ask, well, what do you want to do better on? Right? And then maybe I'd say, okay, let's do better on both, or all of them. And so what this would look like is basically something like, well, right now this is 15% deviation from the district average. I want 10% deviation. right? So they sort of identify where they want to go, and then we search, and then we might find, yes, we can find zones, or we might find, no, we can't find zones. Okay, so we kind of have this ongoing search process. It goes back and forth, and you'll end up with something that looks a little bit like this, right? We have this whole set of zones that they've found as part of this back and forth iterative process. Okay, and what we do is we say, well, some of these zones are going to be better than other zones on all of these non-improvable. It's not possible to do better on all metrics at once. Okay, and so we're going to focus on this set of non-improvable zones. We call these the Pareto efficient ones. Okay. And so that's sort of conceptually what we were doing, but practically how we did this, we didn't just, go to people and ask, like, which constraints do you want to tighten or loosen? Our first version is we built a dashboard, okay, for people to be able to kind of see how all these zones are doing and play around with them. And then after playing around with a whole bunch of different zones, they would give us verbal feedback, and then we would encode those as new optimization constraints, run all of those, put new zones in the dashboard. They would play around with the new zones and then come back to us again. Okay, so as you can tell, this is a very time-consuming process, and it required one of my PhD students to spend a lot of time kind of doing this back and forth and interpreting the optimization constraints. And so that prompted for us a version 2, where we said, what's really good at translation and doesn't have to be a PhD student? LLMs, right? LLMs are really great at translating. And in fact, one of my colleagues at Stanford has shown with this tool Optimus that LLMs can actually reliably and accurately formulate entire optimization problems from natural language prompts, which is really cool because in our case, we're doing something much less complicated. We're just formulating single constraints. Okay, and so this is what this initial prototype of the LLM tool looks like. You're optimizing school zones. You have this slider. You can choose how many zones there should be, how diverse you want the zones to be. And then you can put in natural language, what else you want from zones. And there are sort of these predefined options that it works well for. And then if you just put in whatever you want, sometimes it works, sometimes it doesn't. Okay, but prototype. And then it generates zones and it shows these zones and you can mouse over and kind of look at what's going on in the zones. Okay, so 5 minutes to show you some results of all of this work. The first question you might ask is just, let's go back to the computational question. How do the zones look that we generate using all these approaches? And so on the left, I'm showing you the direct optimization using the big building blocks. This was for the previous policy paper. Approach number 2 is our multi-level optimization approach. Approach number 3 is sort of directly applying relaxed recom. And so one thing that we thought was very interesting is that in this very constrained setting, relaxed recom really doesn't do as well as we thought it would, right? So even visually, looking at this purple map, you can see it kind of has some like visual irregularities. There's like, it says it's contiguous, connected, but there's this, in the purple one, there's really a tiny bridge, if any bridge at all, between what are essentially 2 islands. And then there are also lots of these like dangling tails, which people will look at and think it looks gerrymandered. Then we can also look at how it does in terms of these metrics that we were interested in when we were doing. And so again, I'm just showing you as an example, socioeconomic diversity is measured by deviation from the district average of free reduced price eligibility, as well as seat shortage. So that's percentage of students without a seat in their zone. And I'm going to use the same axes, and the lower left is better. And so you can see if I'm just trying to come up with maps with 6 zones, then the green, which is our multi-level optimization, is a little bit better than direct optimization. But again, the relaxed recom is really not doing very well. And we see this pattern persist across different sizes of zones. Okay, and then finally, the district was also interested in a policy where they don't actually change to new zones. They just redraw the current attendance areas and keep the current policy just as like a benchmark. Okay. And for that, we couldn't actually use any of our approaches I've told you about. And so there's another approach that we developed known as an overlapping recursive approach. That's in the paper. Okay, and so you can see in all of these sort of more refined math programming approaches are doing better than just using the big blocks. Okay, now going to sort of the participatory part. So What I'm showing you here is the result of just using the multi-level optimization and the interactive dashboard. One thing that happened with the interactive dashboard, in addition to being very sort of time consuming, so requiring a lot of stakeholder time and researcher time, it was also super complicated. And so there were lots of staff who were initially willing to help, but in the end, the only ones who could really navigate this huge dashboard were the two data scientists. Okay, and so what I'm showing you is just the results from their interaction. Okay, and so you can see that for 6 zone maps, we're through this process able to generate about 90 zone maps, and these correspond to about 6 different sets of these combinations of balance constraints. Okay? And as the number of zones becomes more, or the zones become smaller, then it becomes harder to find maps that satisfy sort of good enough balance constraints. Okay. And so using these, this is how they built the consideration set. And so then these two staff were able to sort of figure out their preferences over these still quite large sets, sort of first weeding out unacceptable zones and then doing some kind of scoring. Okay. But once you have this consideration set, they've kind of had time to explore, then we kind of view this preference elicitation problem as a little bit more standard. Okay. And then once you have the preferences, again, aggregating the preferences is the next natural thing. We would have to collect preferences from a lot more different stakeholders, which we're hopeful that we can do with LLM tool, and then aggregate them. But again, once we have these rank ordered preferences, aggregating them should be fairly standard. Okay. So just to show you some examples of highly scored zone maps, here's one with 6 zones, 10 zones, 13 zones, and 18 zones. You can see they one thing that's common between them is they kind of try to not split up the Southeast, which was something that had been flagged as potentially not desirable, splitting that Southeast in early participation. And we also sort of had some sort of initial policy takeaways just based on the zones that we found here. So for example, only the really big zones are going to improve on diversity, but then essentially only the smaller zones improve on all proximity metrics. And so, there has to be some sort of trade-off. You can do better on some proximity metrics and diversity, but not all proximity metrics and diversity. Okay. So to sum up, we introduced this iterative framework for allowing stakeholders to participate in the zoning process. This was enabled by novel, faster computational approaches to multi-school zoning. And what I'm really excited about here is a sort of proof of concept using the large language models to enable broader participation in general algorithmic policymaking, right? But in our specific case, helping people to interact with optimization. Okay, and so for our project, some future directions include, we're still working on sort of combining the zoning and choice all into that first step. And then also, we're also currently working on building out the LLM tool to be usable by a broader set of participants and doing a user study. And so I'm really excited about both of those. But more broadly, I think what's, as I already said, the most sort of groundbreaking. I feel like before we didn't have this ability, right, to be able to translate between natural language and optimization or other sort of more complex algorithmic tools without having a researcher in the room. And so I think we're really at this cool moment where we have a new set of tools that we can use to essentially democratize algorithmic policymaking, have a lot more people involved in the weeds of the process. And so I think there are lots of problems just in our school choice setting where we could use that, but I think it can be used more broadly as well. So with that, I will conclude. Thank you.
I thank you for this work. Irene, this was really impressive. I'm thinking about this broader societal and political context where uh, private property taxes account for maybe close to 50% of school funding nationwide, and thinking about like the politics behind the policy, which I'm sure you've thought about deeply. And so that's all set up to say that I can see why the language models would be a potentially exciting form to like increase the access. And perhaps you're already thinking about this in the user study, but how are you broadly thinking about, and can you say more about like evaluating both the accuracy of the LLMs and being able to actually like translate to an optimization problem? I'll have to check out the paper from your colleague. And then the second being, do you think having a technological solution at all might be an impediment to various stakeholders from different neighborhoods? Thanks.
Yeah, two excellent questions. The first question on how do you evaluate the accuracy? Yeah, I would say we're just going to be using the methods that are already developed by Madeline Odell and her group. In that Optimist, they have a series of papers, and so I invite you to read those. And then in terms of the drawbacks of a socio-technical approach, many thoughts. Let me just say a few. First is that for something like districting, you're going to have to use algorithms, right? And so to the extent that we can help make that process more accessible, I think we're improving on things. In terms of which families are going to be able to really have, the time, the desire, the bandwidth to meaningfully participate in something like this. That's something that we have talked a lot about over the years with the school district, and in fact, why we're being very careful to I think there were some great points made yesterday in the panel about, we don't have a right to community access as researchers, right? We're very careful to sort of embed all of our engagement as part of sort of local groups and also in concert with the district's timeline for rolling out the policy, right? We want to talk about it when it's top of mind, when something is about to happen, when the families are thinking about it anyway. And so all that to say that we haven't really had that moment yet when it's right to do that kind of engagement for the zones. And so I don't really have a good sense of who is going to be able to attend. But we have done several rounds of community engagement at sort of a more high level. So there, last summer, one of my students led a very focused round of community engagement, just targeting those areas that are more minority families live, and right, just places where we thought it was useful to get feedback specifically from those families, either because they might be more negatively impacted by the policy or because they've been negatively impacted by student assignment policies in the past. And we had pretty good turnout for those, but we couldn't really use the engagement to do like the zone building because it was too high level, right? When you're just asking people like, what do you want, right? Like, what are the top things that matter to you? Like, do you care more about diversity or distance? You kind of don't really get the level of granularity that is actually usable in zone design. Yeah, so yeah, all I have to say is we've tried to do what we can given the current limitations, but I just don't know how it will really play out once we're actually designing zones. Yeah, I'll stop there, but thank you for the question.
Yeah, yeah, this is really exciting work, and I'm super curious if you have just sort of like, I know you haven't done the full user study, but just like anecdotal observations, kind of like seeing how people interact with the LLM tool. So for example, when people get an output that's not what they want, and they have to sort of like interactively go through some process of trying to make it what they want. Like, and I can imagine that that's like sort of difficult if you don't understand like the sort of the internal representation, basically, that the LLM is translating into, right, to figure out how to debug the system. And I'm really curious, just like if you've seen people sort of like working through that process and like what sort of strategies you think they might be using.
Yeah. So we've had some people sort of play with the demo version. And so what we've learned from that is we definitely need a step going back to the question of evaluation, just making sure that, because there could be many things that go wrong, right? It could be that the constraint itself is not formulated correctly. It could be that once you put in the constraint, it can't solve, right? And there's a lot of other things that could go wrong. But at a minimum, we should be able to, we should have steps to help identify like which of those is going wrong, right? A step where the user can kind of see, oh, like we would have to think about how exactly to do this, but sort of verify that the constraint itself is capturing what they wanted to capture before trying to actually solve it. I mean, the thing that we're expecting to happen is that people will put in a bunch of constraints, and once they're formulated correctly, the answer will be there are no feasible zones, right? That's kind of one of the things we want to happen, because that's generally, you ask people for their top 3 priorities, they name them, and as soon as they name them, you can tell there's not going to be a policy that satisfies this, at least not for like everyone in the district, right? I mean, most people's top priority is I want this particular school in my zone. And so that was also something we had to navigate in a lot of the community engagement, getting like more useful sort of civic-minded feedback. Yeah, and so I think that's also something like showing when is it because the tool is not working versus like you're asking for something that's impossible. That's something we want to be able to very clearly delineate as well. Yeah, but way too preliminary right now to say anything more.